This narrated PowerPoint focuses on the Stefan-Boltzmann law. The Stefan-Boltzmann law is a very important formula that we use when we talk about stars and other objects that emit radiation like a black body. There are two different versions of the Stefan-Boltzmann law on your formula sheet. Both are given in solar units because we're going to compare these objects to our sun to make the numbers a little more easy to handle. Notice that they all relate, both of these versions of the Stefan-Boltzmann law relate three variables: the luminosity, the radius, and the temperature. Again, the luminosity, the radius, and the temperature. So what's the difference? You'll notice that the first version over here solves for L, solves for the luminosity. So if you're given the radius and the temperature and want to solve for the luminosity, this first version is the version that you would want to use. Notice that in the second version, it is solved for the radius. So if you are given the luminosity and the temperature and want to solve for the radius, this second version is the version that you'll want to use. So let's say that we have a star that is 3 times the size of the sun, but is the same temperature. What is its luminosity? So it's a Stefan-Boltzmann law question because we have the size or the radius, we have the temperature, and we have the luminosity. But which of these two versions do we want to use? Well, we're going to solve for the luminosity. So why don't we use the version of the formula which solves for the luminosity? That sounds like it's going to be easier, right? Certainly is. So let's look at what we've got and what we're going to solve for. We are given that the star is 3 times the size of the sun. So R is going to be 3 if the sun's value is 1. You're given that the temperature is the same as the sun. So the temperature is going to be 1 in solar values. So the Stefan-Boltzmann law says that luminosity in solar units is R squared T to the 4th. So this is going to be equal to 3 squared times 1 to the 4th, or 9 times 1 equals 9. So this star has a luminosity that is 9 times the luminosity of the sun. Let's stop and see if this makes sense. The star is the same temperature as our sun. So the temperature doesn't affect it at all. But it's going to come out, it says that it has a size, a radius, that is larger than our sun. If the star is bigger than our sun, doesn't it make sense that it's going to be brighter? Isn't that what we got? We got that the star is 9 times the luminosity of our sun. So this does pass the sniff test. The number makes sense. Let's do a second problem. Another star is twice the temperature of the sun, but only 1/3 the size. What is its luminosity? Again, the first thing we should do is try to figure out which version of the Stefan-Boltzmann law we want to use. Again, in this case, we are also solving for luminosity, so the first version is going to be the easier one to use. So in this problem, we are given that the temperature is twice the temperature of the sun, or 2 solar values, and we're given that the radius is 1/3 the solar value. So the luminosity is going to be the radius squared, T to the 4th. Again, remember, you must do this relative to the sun, but we've been given values that are relative to the sun. So this is going to be 1/3 squared times 2 to the 4th. So this comes out to be 1/9 times 16 1/9 times 16 is 1.8. So this star comes out to be 1.8 times brighter than the sun. Let's see if this makes sense. Well, this star is smaller than our sun, so we might think that it's going to be dimmer. But notice that it's hotter than our sun. And since temperature is raised to the 4th power, and the radius is only raised to the 2nd power, temperature is going to be much more important here. So having twice the temperature more than makes up for the fact that it is only 1/3 the size, and so it makes sense that this star is going to be brighter or more luminous than the sun. This is an example of the third type of problem you might have for the Stefan-Boltzmann law. A third star is twice as hot as the sun, but only has a luminosity of 0.0001 that of the sun. What is its radius? Well, before we go any further, let's think about this. It's hotter than our sun, so we would think that it would probably be brighter. But we see in the problem that it's a lot dimmer than our sun. Why do you think that is? What has to be true about its radius? Well, obviously, if it's hotter than the sun, but it's very dim, it's got to be very small. So we're going to expect an answer for the radius that's very small. Keep that in mind. Now, which version of the formula should we use? Remember, we have two. We have the case where you would solve for the luminosity, and you have the case where you would solve for the radius. In this problem, we want to solve for the radius, so we're going to use the second version of the Stefan-Boltzmann law. So, the second version of the Stefan-Boltzmann law says that the radius is equal to the square root of the luminosity divided by the temperature squared, but remember that it has to be in solar units. It has to be relative to the sun. Well, we're given the luminosity relative to the sun. We're given that it is 0.0001, and we are given the temperature also relative to the sun. We're given that it's twice as hot. So we can go ahead and just plug the numbers in. So we're going to have the square root of 0.0001 divided by 2 squared, and this gives us 0.01 divided by 4, which comes out to be 0.0025. So what does this answer mean? It tells us that the size of this star is 0.0025 the size of our sun. Isn't that what we expected? Remember that this star is hotter than our sun, but it is much dimmer in terms of its energy output. So therefore, we had to get a radius that was small, and indeed we did.